Now, let's begin. A time loop is a hypothetical or theoretical phenomenon in which time does not move strictly forward in a straight line, but instead curves back onto itself, causing events to repeat. In a time loop, a sequence of moments leads back to an earlier point in time, forming a closed cycle. Once the loop begins, the same interval of time is experienced again and again, either exactly the same way or with small variations, depending on the model being considered. At its most basic level, a time loop challenges our everyday understanding of time. In normal human experience, time feels linear. The past is fixed, the present is fleeting, and the future is open. A time loop breaks this linearity. Instead of time flowing like a river from source to ocean, it behaves like a circular track, where the end reconnects to the beginning. When something enters this loop, it is trapped within that circular structure of time. Time loops can be local or global in concept. A local time loop affects only a specific region of space, an object, or an observer. For example, a person might relive the same hour repeatedly while the rest of the universe continues forward. A global time loop, on the other hand, would involve the entire universe repeating a cycle, where the cosmos itself returns to a previous state and replays its evolution. One of the most important distinctions in time loop theory is whether the loop is perfectly repeating or mutable. In a perfectly repeating loop, every event happens in exactly the same way each cycle. The same decisions are made, the same words are spoken, and the same outcomes occur with no deviation. This type of loop implies strict determinism, where free will may be an illusion because the future is already fixed by the structure of the loop itself. Mutable loops are more complex. In these, each cycle allows for slight changes. A person trapped in such a loop might retain memory from previous cycles and attempt to alter events. However, even in mutable loops, there may be constraints that prevent major changes, as the structure of time may resist paradoxes or self-contradictions. A crucial concept connected to time loops is the idea of closed time-like curves, often abbreviated as CTCs. In physics, a time-like curve represents a path through spacetime that a particle with mass could follow. A closed time-like curve is one that loops back to its starting point in time as well as space. If such curves exist, they would mathematically allow time loops, making it possible for an object or observer to return to its own past without breaking the local rules of space-time motion. Time loops are often confused with simple time travel, but they are not exactly the same. Traditional time travel usually involves moving from one point in time to another and continuing forward from there. A time loop, in contrast, is self-contained. Once inside, time does not progress beyond a certain boundary. The system resets or reconnects to an earlier moment, either automatically or due to the geometry of space-time itself. Another key feature of time loops is the problem of memory and causality. In some loop models, the person inside the loop remembers previous cycles, while the rest of the environment resets. In others, memory is erased at the reset point, making the loop indistinguishable from normal time flow for those trapped within it. From an external viewpoint, however, the loop still exists as a repeating structure in space-time. Causality becomes deeply complex in time loops. Normally, causes precede effects. In a time loop, an event can be both cause and effect of itself. This leads to what are known as causal loops, where information or objects exist without a clear point of origin. For example, an idea might be learned in the future and brought back to the past, only to become the very source of that same idea. Philosophically, time loops raise profound questions about identity, choice, and responsibility. If a person repeats the same actions infinitely, are they morally responsible for those actions each time? If they cannot escape the loop, does blame or praise lose meaning? These questions show that time loops are not just scientific curiosities, but also deep conceptual challenges to how we understand reality. In summary, a time loop is a theoretical structure where time folds back on itself, creating repetition rather than progression. It can be rigid or flexible, local or universal, deterministic or partially changeable. While often explored in fiction, The idea is rooted in serious discussions about spacetime, causality, and the nature of time itself. Understanding what time loops are is the first step before examining whether such structures could exist in space and in the natural universe. Time loops can be classified into several distinct types based on how time behaves within the loop, how information is preserved, and how the loop interacts with the rest of spacetime. Understanding these types is essential before exploring whether time loops could exist in the physical universe, because each type places different demands on the laws of physics and causality. One of the most discussed categories is the fixed time loop. In a fixed loop, every event is locked into a single, unchangeable sequence. No matter how many times the loop repeats, the same actions occur in the same order. Even if an observer inside the loop believes they are making new choices, those choices are already part of the loop structure. From a physics standpoint, this aligns with a deterministic universe, where the future is as fixed as the past. In such a loop, paradoxes are avoided because nothing ever truly changes. Closely related to fixed loops is the idea of the self-consistent loop. This concept is often associated with the principle that any events occurring within a time loop must be internally consistent. In other words, the loop cannot produce contradictions. If a person travels back in time within a loop, their actions in the past must already be part of history. This avoids classic paradoxes, such as preventing one's own existence. Instead, the loop ensures that whatever happens has always happened. Another major category is the dynamic or adaptive time loop. In these loops, small changes are possible from one cycle to the next. A person may retain memories of previous iterations and attempt to influence events differently. However, even in adaptive loops, there are often constraints that limit how much can change. Large-scale outcomes may remain the same, while minor details shift. This suggests that time may have an underlying structure that resists drastic alterations, even when flexibility exists. There are also observer-dependent loops, where the loop exists only for certain observers. From the perspective of someone inside the loop, time is repeating. From external perspective, time may appear to move forward normally. This raises the idea that time loops might not be absolute features of the universe, but relative phenomena, dependent on the path an observer takes through space-time. Another important distinction is between closed informational loops and closed physical loops. In an informational loop, only information travels around the loop. For example, knowledge, instructions, or memories might pass from the future to the past, influencing events. In a physical loop, matter and energy themselves follow a closed path in time. Physical loops are far more demanding in terms of physics because they require space-time itself to allow matter to move backward in time along a stable trajectory. Time loops can also be finite or infinite. A finite loop repeats a limited number of times before breaking or resolving. An infinite loop repeats endlessly with no exit. Infinite loops raise questions about entropy and energy. In normal thermodynamics, systems tend to move toward disorder over time. If a loop repeats infinitely, does entropy reset each cycle, or does it accumulate? This question becomes critical when considering whether time loops could exist in nature without violating fundamental physical laws. Another structural aspect of time loops is the reset mechanism. Some loops reset abruptly, snapping back to the starting point once a certain condition is met. Others transition smoothly, where the end of the loop gradually merges into the beginning. The reset could be triggered by an event, a boundary in space-time, or the geometry of the loop itself. The nature of this reset determines whether the loop feels artificial or natural from within. A particularly intriguing idea is the bootstrap loop, a type of causal loop where objects or information have no clear origin. An object might be taken back in time and later discovered by its past self, becoming the very object that was sent back. In such cases, the object exists in a closed loop of causality, with no external starting point. While logically strange, such loops are not forbidden by the equations of certain physical theories. From a psychological and experiential perspective, time loops raise questions about consciousness. If a person relives the same events repeatedly, but retains memory. Their subjective experience of time becomes detached from objective time. They may feel as though years or centuries have passed, even though only a short interval exists externally. This separation between internal and external time is important when discussing loops in a relativistic universe. In summary, time loops come in many forms, ranging from rigid and deterministic to flexible and adaptive. They can involve information alone or full physical systems, affect only certain observers or entire regions of space-time, and repeat finitely or infinitely. Each type places different demands on physics, causality, and entropy. Understanding these distinctions prepares us to examine whether any of these loop structures could plausibly arise in space and in the natural fabric of the universe. The idea of time loops does not arise solely from imagination or fiction. It emerges naturally when scientists explore the deeper implications of modern physics, especially theories that describe space and time as a unified structure rather than separate entities. To understand why time loops are even considered possible, it is necessary to examine how time behaves in these theoretical frameworks. In classical physics, time is absolute and universal. It flows at the same rate everywhere and for everyone, independent of motion or gravity. Under this model, time loops are impossible because time cannot bend, slow down, or reverse. However, this picture was fundamentally altered by the development of relativity, which showed that time is not fixed but deeply connected to space and influenced by matter and energy. According to the theory of relativity, space and time form a four-dimensional structure known as spacetime. Objects move through spacetime along paths determined by gravity and motion. Crucially, gravity is not a force in the traditional sense, but a curvature of spacetime caused by mass and energy. This curvature affects not only the motion of objects through space, but also the flow of time itself. When spacetime becomes strongly curved, unusual paths through time become mathematically possible. Under certain extreme conditions, the equations describing spacetime allow paths that curve backward in time and reconnect with their own past. These paths are the theoretical basis for time loops. They do not require breaking the laws of physics locally. Instead, they rely on the global structure of spacetime being unusual. One of the key mathematical ideas behind time loops is the concept of time-like paths. A time-like path is one that any object with mass could follow while always moving slower than light. In ordinary spacetime, these paths move steadily forward in time. However, certain spacetime geometries permit time-like paths that curve around and return to their starting point in time. This is where the possibility of loops arises. The presence of such paths suggests that time, under the right conditions, might behave more like a dimension that can be navigated rather than a one-way flow. Just as one can walk north, south, east, or west in space, the geometry of spacetime might allow unusual routes that lead back to earlier moments. Time loops, in this sense, are not violations of physics, but extreme consequences of its mathematical structure. Another important foundation is the role of symmetry in physical laws. Many fundamental laws are symmetric with respect to time. This means that, at a basic level, the equations often work just as well if time runs forward or backward. While everyday processes break this symmetry due to entropy, the underlying equations themselves do not strictly forbid backward time behavior. This opens conceptual space for time loops, at least at the microscopic or mathematical level. The concept of global versus local physics is also crucial. Locally, the laws of physics might look perfectly normal inside a time loop. An observer would experience gravity, motion, and energy conservation just as usual. The strange behavior only appears when considering the entire structure of space-time as a whole. From this perspective, time loops are global features that do not necessarily cause local inconsistencies. Another reason time loops are taken seriously is that physics often reveals possibilities that initially seem absurd but later gain acceptance. Black holes, gravitational waves, and the expansion of the universe were once purely theoretical predictions that seemed almost fantastical. Time loops occupy a similar position. They are allowed by certain equations, even if we do not yet know whether nature realizes them. Quantum theory also contributes indirectly to the plausibility of time loops. At the quantum level, particles do not follow single, well-defined paths, but exist in superpositions of possibilities. This probabilistic nature of reality suggests that time itself may not be as rigid as once believed. While quantum theory does not directly predict macroscopic time loops, it weakens the assumption that time must always behave classically. Furthermore, the combination of quantum theory with space-time curvature leads to unresolved questions. In regimes where gravity and quantum effects are both strong, such as near extremely dense objects, our current theories are incomplete. Some proposed models of quantum gravity suggest exotic space-time structures where classical notions of time break down, potentially allowing loop-like behavior. Importantly, the theoretical allowance of time loops does not mean they are easy to create or common. The conditions required appear to be extreme, involving enormous energy densities or unusual space-time configurations. Nevertheless, the fact that respected physical theories permit such structures means that time loops cannot be dismissed outright as impossible. In summary, time loops are considered possible because modern physics treats time as flexible, shaped by motion, gravity, and space-time geometry. Under certain extreme conditions, the mathematical structure of space-time allows paths that return to the past, forming loops. These ideas are rooted in serious theoretical work rather than pure speculation, making time loops a legitimate topic of scientific inquiry. One of the strongest objections to time loops arises from the concept of causality, the principle that causes precede effects. Causality is deeply embedded in both human intuition and scientific reasoning. Any theory that allows time loops must confront the question of whether cause and effect relationships can remain meaningful when events influence their own past. In a time loop, causality does not necessarily disappear, but becomes circular. An event may be caused by another event that lies in its future, which in turn depends on the original event. This circular structure challenges the idea of a clear temporal origin. However, circular causality is not logically inconsistent by itself. It is unfamiliar, but unfamiliarity does not equal impossibility. One of the most discussed issues is the so-called grandfather paradox, where a time traveler goes back and prevents their own existence. In a strict time loop, this paradox cannot occur because the loop enforces consistency. Any action taken in the past must already be part of history. If the traveler exists in the future, then their actions in the past cannot eliminate that future. This suggests that time loops may protect causality by restricting what can happen. This leads to the idea of self-consistency as a governing rule of time loops. Under this rule, only those events that are logically consistent can occur within a loop. Attempts to create contradictions would simply fail, either through unlikely coincidences or through physical constraints that prevent paradoxical outcomes. In this view, the universe behaves in a way that preserves consistency, even if time itself bends. Another challenge involves free will. If a time loop is fixed and self-consistent, it may seem that individuals inside the loop have no genuine freedom to choose differently. Their actions are already determined by the structure of the loop. Some interpretations accept this as a consequence of determinism. Others argue that free will may still exist at a subjective level, even if the outcomes are fixed. Memory plays a crucial role in how time loops are experienced. If memories reset at the beginning of each cycle, then from the inside, the loop is indistinguishable from normal time. No paradox arises because no one remembers previous cycles. If memory persists, however, then the psychological experience of time diverges sharply from physical time. An individual could accumulate knowledge and emotional weight across many repetitions, even though the external timeline remains short. Entropy is another major limitation. In ordinary physics, entropy tends to increase over time. This provides the arrow of time, distinguishing past from future. A time loop seems to violate this tendency by repeating a low entropy state over and over. For a loop to exist, either entropy must reset at each cycle or the loop must be arranged so that entropy is constant along the closed path. Both options require unusual conditions, suggesting that time loops would be extremely rare or tightly constrained. Energy conservation also raises questions. If a system repeats endlessly, does it require an external energy source to reset itself? In a perfectly closed space-time loop, energy conservation can still hold because the system does not gain or lose energy globally. Locally, however, maintaining stability over many cycles may be difficult. Small perturbations could accumulate and destabilize the loop unless some mechanism enforces exact repetition. Another limitation concerns stability. Even if space-time allows a time loop mathematically, that loop may be unstable. Tiny disturbances, such as passing particles or quantum fluctuations, could disrupt the delicate geometry needed to sustain the loop. This instability suggests that time loops, if they exist, might be fleeting or microscopic rather than large, macroscopic structures. There is also the issue of chronology protection, a concept proposed to explain why time loops might not occur in nature, even if they are allowed mathematically. According to this idea, the laws of physics may contain mechanisms that prevent the formation of time loops, preserving a consistent causal order. These mechanisms could involve quantum effects that become dominant whenever a loop is about to form, effectively destroying it. Importantly, none of these limitations definitively rule out time loops. Instead, they define the boundaries within which loops might exist. They suggest that time loops would require exceptional conditions and may be constrained in size, duration, or accessibility. They also imply that our everyday experience of time is protected from paradoxes by deeper physical principles. In summary, time loops push the concept of causality to its limits, but do not necessarily break it. By enforcing self-consistency, restricting paradoxical actions, and requiring extreme conditions, the universe may allow loops in theory while making them extraordinarily difficult to realize. These limitations prepare us to transition from abstract theory to a more grounded question. Could time loops actually exist in space and in nature? When the discussion shifts from theory to nature, the central question becomes whether the universe can actually create the conditions required for time loops. Physics does not treat time as an abstract background, but as an active dimension shaped by mass, energy, and motion. If time loops exist in nature, they would arise not from artificial manipulation, but from extreme cosmic structures where space-time is distorted in unusual ways. One of the most important factors in the possible existence of time loops in space is electrica, a space-time geometry electrica. In regions where gravity is weak, space-time is nearly flat, and time behaves in a familiar, forward-flowing manner. However, in regions of intense gravity, space-time can curve dramatically. This curvature does not only bend space, it also affects the direction and rate at which time flows. Certain theoretical space-time geometries allow paths that curve back in time. These geometries are not invented arbitrarily. They are solutions to the equations that describe gravity and space-time. In such solutions, time is not globally ordered in a single forward direction. Instead, there may exist regions where an object following a physically allowed path could return to its own past. One class of cosmic objects often discussed in this context is electrica, extremely rotating massive bodies electrica. Rotation twists space-time around the object, a phenomenon sometimes described as the dragging of space-time. If this twisting becomes strong enough, the time dimension itself could be affected in such a way that closed paths in time become possible. In these scenarios, time loops would not be universal but localized near the rotating structure. Another potential source of time loops in space involves electrica, exotic space-time structures electrica predicted by advanced gravitational models. These structures are not ordinary stars or planets, but hypothetical configurations where space-time is stretched, compressed, or connected in unusual ways. In such environments, the distinction between past and future may blur, allowing time to curve back on itself. Cosmic scale gravity also plays a role. In the early universe, conditions were vastly different from today. Matter and energy densities were extreme, and space-time curvature was intense. Some theories suggest that during these early moments, the structure of time itself may have been more flexible. If time loops could exist at all, the early universe might have provided the right environment for them to form, even if only briefly. Another important aspect is the electrical relationship between space and time paths electrica. In relativity, objects move through space-time along paths determined by geometry rather than forces in the classical sense. If the geometry allows a closed path, then a time loop exists in principle. The object following that path would not experience anything locally unusual. It would simply be moving naturally through space-time. The loop would only become apparent when considering the full path from a global perspective. However, the existence of a mathematically allowed path does not guarantee physical reality. The universe may forbid such paths through stability constraints or quantum effects. Still, the fact that natural laws allow the equations to describe these geometries means that time loops cannot be dismissed as purely fictional. They remain hypothetical, but grounded in real physical reasoning. Astrophysical observations so far have not confirmed the existence of any natural time loops. This is not surprising, because detecting such structures would be extraordinarily difficult. A time loop would likely be confined to a small region of extreme gravity, far beyond direct observation. Its effects on surrounding space might be subtle or masked by other phenomena. Another possibility is that time loops exist only at microscopic scales. At these scales, quantum effects dominate, and space-time may not behave smoothly. If microscopic loops exist, they would not allow a macroscopic object to travel back in time, but could still influence fundamental processes in subtle ways. Such loops would be part of the deep structure of space-time rather than observable features of the cosmos. In summary, the possible existence of time loops in space depends on whether the universe can naturally produce extreme space-time geometries. Rotating massive objects, exotic space-time structures, and early universe conditions all provide theoretical pathways for such loops to form. While no direct evidence exists, the laws of physics do not categorically forbid them. This keeps the idea of natural time loops within the realm of serious scientific exploration rather than pure speculation. To move closer to the question of whether time loops could exist in the real universe, it is necessary to examine specific cosmic phenomena that naturally push space-time to its limits. The universe contains environments where gravity, motion, and energy reach extremes far beyond anything achievable by human technology. These environments provide the most realistic settings in which time loops, if they exist at all, could emerge. One of the most important natural mechanisms involves electrica, extreme rotation, combined with massive gravity, electrica. When a massive object rotates, it does not merely spin within space. It twists space-time itself. This twisting effect increases dramatically as the object becomes denser and rotates faster. In theoretical models, if this twisting becomes strong enough, the time dimension can be affected in such a way that future-directed paths begin to tilt backward, allowing closed loops in time to form in a localized region. Another natural phenomenon often discussed is the presence of electrica high-energy cosmic fields electrica. In certain regions of space, especially near very dense or energetic objects, fields associated with gravity and other fundamental interactions can become extraordinarily intense. These fields influence how space-time is shaped and how particles move through it. Under rare conditions, the combined influence of these fields might distort space-time in a way that allows time to loop locally without affecting the broader universe. The early universe remains one of the most promising natural laboratories for exotic time behavior. Shortly after the universe began expanding, energy densities were immense, and space-time itself was highly dynamic. During this period, the clear distinction between past and future may not have been fully established. Some theoretical models suggest that temporary time loops could have formed during this chaotic phase, later disappearing as the universe cooled and expanded. Another possible mechanism involves electrica features of space-time electrica. Topology concerns the global shape and connectivity of space rather than its local curvature. Even if space-time is smooth and well-behaved locally, its global structure could allow paths that loop in time. In such cases, time loops would arise not from extreme gravity at a point, but from the overall shape of space-time across large distances. Quantum effects may also play a role. At very small scales, space-time is thought to fluctuate due to quantum uncertainty. These fluctuations could create transient structures where the usual rules of time temporarily break down. While such loops would be extremely small and short-lived, they could still exist as natural features of space-time. If so, time loops might be common at microscopic scales while remaining inaccessible to macroscopic objects. Despite these possibilities, nature appears to strongly resist the formation of large, stable time loops. One reason is that extreme conditions often lead to instability. Small disturbances can grow rapidly in such environments, disrupting any delicate structure required to maintain a loop. Additionally, quantum effects may become dominant whenever space-time approaches a configuration that allows time to loop, preventing the loop from stabilizing. Observational evidence also places constraints on the existence of time loops. If large, persistent loops were common, they might leave detectable signatures in cosmic radiation or gravitational phenomena. So far, no such signatures have been identified. This suggests that if time loops exist, they are either rare, hidden in inaccessible regions, or confined to scales too small to observe directly. Another important consideration is the relationship between time loops and cosmic evolution. The universe shows a clear arrow of time, marked by increasing entropy and irreversible processes. Any natural time loop would need to exist in a way that does not disrupt this overall trend. This further limits the types of loops that could exist, favoring localized or microscopic structures over global, universe-wide loops. In conclusion, several natural mechanisms could, in theory, support the existence of time loops in space. Extreme rotation, intense gravitational and energy fields, early universe conditions, space-time topology, and quantum fluctuations all provide plausible pathways. However, strong constraints from stability, entropy, and observation suggest that if time loops exist in nature, they are likely rare, localized, and subtle. They would be extraordinary features of the universe rather than common or easily accessible phenomena. As the exploration of time loops reaches its final stage, the focus turns to the boundaries imposed by nature itself and what these boundaries reveal about the universe. Even if time loops are mathematically allowed and theoretically possible under extreme conditions, the universe may still restrict their formation through deep physical principles that preserve consistency and stability on cosmic scales. One of the strongest natural limits comes from the overall structure of cosmic time. The universe displays a clear directional flow, often called the arrow of time, driven by increasing entropy. Galaxies form, stars age, and energy spreads out irreversibly. Any natural time loop must exist without violating this global trend. This suggests that if loops exist, they cannot dominate or override the universe's large-scale temporal evolution. Instead, they would be isolated features, embedded within a broader, forward-moving cosmic timeline. Another major limitation is electrica quantum instability electrica. When space-time is pushed toward configurations that allow time to loop, quantum effects are expected to become extremely strong. These effects could generate violent fluctuations that destabilize the loop before it fully forms. In this sense, quantum physics may act as a safeguard preventing large-scale violations of causality while still allowing the equations of gravity to remain mathematically consistent. Observational challenges further restrict our ability to confirm time loops. Regions where loops might exist are likely hidden behind extreme gravitational environments or confined to microscopic scales. Even if a time loop were present near a distant cosmic object, distinguishing its effects from other known phenomena would be extraordinarily difficult. Many of the signals we could observe, such as gravitational distortions or energy emissions, can be explained by more conventional astrophysical processes. There is also the issue of electrica accessibility, electrica. A time loop may exist in spacetime without being reachable by any realistic physical trajectory. In such cases, the loop is a mathematical feature rather than a physically usable one. Objects and observers may be unable to enter or interact with the loop due to energy constraints or spacetime barriers. This further reduces the likelihood of observable or exploitable time loops in nature. From a cosmic perspective, time loops challenge the assumption that time must always have a single, universal order. Even if loops are rare or hidden, their theoretical existence suggests that time is more flexible than everyday experience implies. The universe may allow complex temporal structures while still preserving overall consistency and causality. Time loops also force a reevaluation of causation itself. In a universe where loops are possible, cause and effect may not always follow a simple linear sequence. Instead, causality could be global and self-consistent, where events are linked in networks rather than chains. This does not destroy causality, but reframes it in a broader, more interconnected way. Importantly, the absence of evidence for time loops does not equate to evidence of absence. Many aspects of the universe were once invisible or unknowable due to technological limitations. Time loops, if they exist, may remain beyond detection for the foreseeable future. Their role may be more conceptual than practical, shaping how physicists think about time rather than offering a means of travel to the past. In the final analysis, time loops occupy a unique position in scientific thought. They sit at the intersection of gravity, quantum theory, and cosmology, highlighting the gaps in our understanding of time itself. Whether or not nature realizes them, their study reveals the extraordinary flexibility and depth of spacetime as described by modern physics. Time loops are not mere fantasy. They arise naturally from serious physical theories that treat time as a dimension shaped by spacetime geometry. Modern physics allows, in principle, paths through spacetime that return to the past under extreme conditions. There are multiple types of time loops, ranging from rigid and self-consistent to adaptive and observer-dependent, each placing different demands on causality, memory, and entropy. The universe provides environments where time behaves unusually, especially in regions of extreme gravity, rotation, and energy. These environments make time loops theoretically possible, but extraordinarily rare. Strong natural limits, including entropy, quantum instability, and cosmic evolution, likely prevent large, stable, and accessible time loops from forming in nature. No direct observational evidence for time loops currently exists, and detecting them would be extremely challenging due to their likely scale and location. The true importance of time loops lies in what they teach us about time itself. That time may not be strictly linear, absolute, or universal, but a flexible feature of a dynamic spacetime. In conclusion, time loops remain a profound and unresolved possibility. They may never be used or observed, but their existence within the boundaries of physical theory shows that the universe is far stranger and more subtle than everyday experience suggests. This understanding leaves the audience with a sense of mystery, depth, and intellectual satisfaction, knowing that even time itself may hold secrets yet to be discovered.